Students, good morning. Today I am going to discuss about the differential changes in internal energy. Differential changes in internal energy. Deriving this equation is much more useful in estimating the differential changes in internal energy for a single compressible substance or single compressible fluids. For that, internal energy U is the function of temperature and volume. Internal energy U is assumed to be function of temperature and volume. If we assume internal energy is the function of temperature and volume, then the total differential change, the total differential change in internal energy du is equal to dou u by dou t at constant volume into dt plus dou u by dou v at constant temperature into dV. Clear? In particular, know that dou u by dou t is equal to heat capacity at constant volume. Hence, this equation becomes total differential changes in internal is equal to Cv into dt plus dou u by dou v at constant temperature into dV. Now, I am going to replace this dou u by dou v at constant temperature using fundamental property relations as well as Maxwell's relation. For application of these two, again entropy is assumed to be a function of temperature and volume. In order to replace this dou u by dou v, I am going to assume entropy S is the function of temperature and volume. If we assume entropy is the function of temperature and volume, then the total differential change, the total differential change in entropy is ds is equal to dou s divided by dou t at constant volume into dt plus dou s by dou v at constant temperature into dV. Clear? Changes in entropy, total differential changes in entropy is equal to dou s by dou t at constant volume into dt plus dou s by dou v at constant temperature in dV. See this equation. From the fundamental property relations, du is equal to T ds minus P into dV. Now I am going to substitute this ds in this equation. Hence, changes in internal energy du is equal to T times of dou s by dou t at constant volume into dt plus dou s by dou v at constant temperature into dV minus P into dV. Here, again this equation becomes changes in internal energy du is equal to T times of dou s by dou t into a constant volume into dt. T times of dou s divided by dou T at constant volume into dt plus T times of dou S by dou U at constant temperature into dV. T times of dou S by dou V at constant temperature into dV minus of P dV minus of P into dV. dV are common terms. Hence this equation becomes du is equal to T times of dou S divided by dou T at constant volume into dt plus T times of dou S by dou V at constant temperature minus P into dV. Now the equation is ready. What I am going to do now is I am going to equate the coefficients of dt and dv with this equation. Clear? So du is equal to Cv into dt plus dou u by dou v at constant temperature into dv. I am going to equate the coefficients of equating the coefficients of dt, coefficients of dt and dv. Clear? dt, hence I am going to equate this 1. So T times of dou S divided by dou T at constant volume is equal to Cv. This equation gives dou S by dou T at constant volume is equal to Cv by dt. This is an important information. While you know that heat capacity at constant volume process Cv and temperature, it is easy to estimate the changes in entropy with respect to temperature at constant volume. This is the important information. Next, dv. So T times of dou S by dou V into T. T times of dou S divided by dou V into T minus P is equal to dou U by dou V at a constant temperature. Clear? Now I am going to change this dou S by dou V at constant temperature by using Maxwell's relation. Dou S by dou V at constant temperature is equal to dou P by dou T at constant volume. So T into dou P divided by dou T at constant volume minus P is equal to dou U divided by dou V at constant temperature. Now I am going to substitute this value in this equation. Clear? So total differential changes in internal energy. Total differential changes in internal energy du is equal to Cv into dt plus T times of dou P divided by dou T at constant volume minus P into dV. This equation is used to find the differential change or total differential change in internal energy for a single compressible fluid or substance. This equation is much more important in estimating or determining differential changes in internal energy for a single compressible fluid or a single compressible system. Thank you.